Hello, my dear children. Welcome to the mathematics class. Today we are going to discuss application of derivatives. Application of derivatives. In this chapter, in the exercise 6.2, we are going to discuss the topic increasing or decreasing function. This exercise is based on this concept increasing or decreasing function. Okay, my dear children, we discuss all these 5 points. We are going to discuss these 5 points. See the first point, analytical definition of increasing or decreasing function. We discuss how the function is said to be, when the function is said to be increasing function or decreasing function analytically. Okay, my children. Now come to the second point. In this second point, first derivative test for increasing or decreasing function. How the concept of derivative is used to test the increasing or decreasing of a function. Okay, my children, we discuss in this point too. Now come to third point, constant function. Which function is said to be a constant function? And next, fourth point, monotonic function. We define monotonic function. And fifth one, steps for finding the intervals of increasing and or decreasing function. This is very important point, my dear children, for the exercise 6.2. These steps are very important. Okay, my dear children, listen carefully. Are you ready to listen the class, my dear children? Right. Now come to the first point, that is analytical definition of increasing or decreasing function on an interval. Okay, my dear children, see this definition, but we frequently not using, very rarely we use this definition, but just understand this definition. Okay, my children, let I be an open interval contained in the domain of a real valued function f. Let us consider an open interval is there in the domain of the real valued function f. Then f is said to be increasing on interval I if x1 less than x2 in interval I implies f of x1 is less than or equal to f of x2 for all x1 comma x2 belongs to I. Okay, my children, if x1 is less than x2 implies f of x1 is less than or equal to f of x2. If this condition is satisfied, then the function is said to be increasing function. Understood this definition, my children? Right. Now come to this second point, strictly increasing on interval I. If x1 less than x2 in interval I implies f of x1 is less than f of x2 for all x1 comma x2 belongs to interval I. See the difference between first point and second point. Here less than or equal to is given, here the less than sign only given. Understood the difference? You observed this difference, my dear children. See here we say that f is increasing function, whereas in this case f is said to be strictly increasing function on the interval I. Okay, my dear children? Right. Now come to the third point, decreasing on interval I. F is said to be decreasing on the interval I if x1 is less than x2 in the interval I implies f of x1 greater than or equal to f of x2 for all x1 comma x2 belong to I, interval I. So it's a reverse. Here less than symbol is there, here less than or equal to, it's opposite. Here increasing. What is the opposite word for increasing? Decreasing. So we take its reverse direction. So f of x1 greater than or equal to f of x2. Then the function is said to be decreasing on the interval I. Understood this definition, my dear children? Right. Now come to the third point, the function f is said to be strictly decreasing on the interval I if x1 is less than x2 in the interval I. Implies that f of x1 is greater than f of x2 for all x1 comma x2 belongs to interval I. Okay, my children. Right. Now we represent some functions graphically in the following figures as shown below. See the figures here. See this first diagram, first figure. This is the graph of the function y is equal to f of x. In this case, this function is said to be increasing function. Whereas if you observe this graph y is equal to f of x, this is the graph of the function y is equal to f of x. In this case, this function is said to be strictly increasing function. Here there is some breaks are there. Here see there up to here, again turning is there, again from here, from this point again it is taking turning, but here there is no turning, there is no jerks in this graph. Understood this graphs, my dear children? Right. Now observe the third figure. See the graph of this function y is equal to f of x is like this. In this case, the function f is said to be decreasing function. In general, we study the graph of the function from left to right, in which direction the curve is moving. Okay, my dear children, not from right to left. Don't study the curve from right to left, from left to right only. Okay, my dear children. Similarly, observe the figure 4, fourth figure. See this figure. This is a graph of the function y is equal to f of x. Here no jerks is there, whereas here jerk is there. Here it is taking a turning. Here at this point it is again taking a turning, but here there is no turning. Completely purely curve. Okay, my dear children. So in this case, the function f is said to be strictly decreasing function. Now this last figure. Observe this figure, my dear children. Here in this interval we can't say whether it is decreasing or increasing. So see here, from this point to this point increasing, again from this point to this point decreasing, and from this point to this point increasing. So in the given interval it is decreasing, again increasing. So in this case we say that neither the function f is neither increasing nor decreasing function. Understood these 5 cases, my dear children? Right. In the first point we have discussed the definition of increasing or decreasing function analytically. Now come to the second point, my dear children. Here we use the concept of derivative, that is first derivative test. This is called first derivative test for increasing or decreasing function. With the help of the concept of derivative, we can say that whether the given function is increasing function or decreasing function in the given interval. Okay, my dear children, listen this point, my dear children, carefully. Let f be continuous on closed interval a comma b and differentiable on the open interval a comma b. You have studied, you have seen the sentence in the mean value theorem, isn't it, my dear children? F is continuous on the closed interval a comma b and it is differentiable on the open interval a comma b. Rolle's theorem and mean value theorem. In the theorems we have studied these sentences, we got that sentences, same sentences, isn't it or not, my dear children? Right. Now come to the first point. F is increasing in the interval a comma b, in the closed interval a comma b, if f dash of x greater than 0 for each x belongs to open interval a comma b. Understood this point, my dear children? Right. We have to find the derivative of the given function and we have to check the values within the interval, and we substitute in f dash of x. If it is greater than 0, means if it is a positive number, then we say that f is increasing function. In the opposite meaning, second point, f is decreasing in the closed interval a comma b if f dash of x is less than 0. If you substitute the values between these two numbers in the f dash of x, if you get less than 0 means a negative value for each x belongs to open interval a comma b between these two numbers. Okay, my children, understood? Then the function is said to be decreasing function. So on the whole, derivative of the given function is very important. Okay, my children. After that, we have to substitute any number between the interval between these two numbers, between these two endpoints. We can select any number and we have to substitute that number in f dash of x. After substituting that number, if the resultant number is a positive number, remember this point, my children, this is very important. If the resultant number is a positive number, then we say that f is an increasing function. On the other hand, if we get a negative number, then we say that f is said to be decreasing function. Okay, my children, understood? Right. Now come to the third point. F is said to be constant function in the closed interval a comma b if f dash of x is equal to 0. See here, here greater than 0, here is less than 0, here is equal to 0 for every x belongs to open interval a comma b. Understood this point, my children? Then the function is said to be constant function. Remember these 2 points, my children. F dash of x greater than 0 means the function is said to be increasing function. If f dash of x is less than 0, then the function is said to be decreasing function. Most of the cases we get this case or this case, not constant function. Very rare case. That is a very rare case. Okay, my children, understood? Right. Now come to the next point, that is monotonic function. What is meant by monotonic function? By monotonic function f of x in the interval I, we mean that f is either only increasing in the interval I or only decreasing in the interval I. Then the function is said to be monotonic function. Either it should be increasing in the interval I or it may be decreasing in the interval I. That is said to be monotonic function. Understood this definition, my children? Right. Now come to the last point. This is very important point for this exercise 6.2. Without understanding this point, we can't solve the questions in the exercise 6.2. My dear children, listen carefully. Steps for finding the intervals of increasing and or decreasing of a function. Sometimes they will give the interval and they will ask you check whether the given function is increasing function or decreasing function. And sometimes we have to find the intervals. We have to find the intervals of increasing or decreasing of the function. In that case, this point is very, very useful. Okay, my dear children, we follow this algorithm. Step 1. First, we have to consider the function y is equal to f of x. We have to assume that y is equal to f of x. Given function y is equal to f of x. And step 2, we have to find f dash of x. We have to find the derivative of the given function. What is meant by f dash of x? Yes, derivative of the given function. Understood this step 2, my children? Right. Now come to step 3. Put f dash of x is equal to 0. Means we have to write this equation. They don't give this equation. We have to write this equation and solve it to get the critical points. After solving this equation, you get some values for x. Isn't it or not, my children? Yes. That values are said to be critical points. These are nothing but the solution set of the equation f dash of x is equal to 0. Critical points are nothing but the values of x which satisfy this equation f dash of x is equal to 0. Understood this step 3, my dear children? Right. Now come to the last step, step 4. The values of x for which f dash of x is greater than 0, then the function f is said to be increasing. Okay, my dear children. And the values of x for which f dash of x is less than 0, f of x is said to be decreasing function. Understood this point, my dear children? We follow these 4 steps. Remember these 4 steps well, my dear children. These are very useful steps for solving the sums in exercise 6.2. Okay, my dear children? Right. Concepts of exercise 6.2 was over. They were completed. Now we are going to start the sums in exercise 6.2. Are you ready to start the exercise 6.2, my dear children? Right. See page number 205. Page number 205. See the first question. Question number 1. Show that the function given by f of x is equal to 3x plus 17 is strictly increasing on R. Understood this question, my dear children? Don't confuse here. Strictly increasing or increasing. Both can be used with the same meaning. Both mean the same. Don't be confused here. Strictly increasing, sometimes they will use the word increasing. Don't be confused, my dear children. Okay, right. Now let us write the given function. What is given function here? F of x. F of x is equal to 3x plus 17. With the help of first derivative test throughout this exercise, I told you previously that last point is very important. First derivative test. Okay, my dear children. So with the help of first derivative test, we verify and we show that, we prove that given function is strictly increasing. Okay, my dear children. For that we have to differentiate with respect to x. Okay, my dear children. Then what is the differential operator? Yes, d by dx. So I wrote the differential operator d by dx on both sides. This implies d by dx of f of x is equal to d by dx of 3x plus 17. Understood this step, my dear children? Right. This implies, come to the LHS part. What is the d by dx of f of x? How do you denote d by dx of f of x? Yes, f dash of x. D by dx of f of x is denoted by f dash of x. Do you remember this point, my children? Right. Is equal to, come to RHS, d by dx of 3x plus 17. Two terms are there. I told you many times, if there are two terms, if you want to find the derivative of that function, we can find the derivative of the function by finding the derivatives of each and every term separately and adding them. So d by dx of 3x plus d by dx of 17, just like a distributive property. Just remember like that. Okay, my children? Right. Because d by dx of f of x is equal to f dash of x. We use this notation. Okay, my children? Understood this step? Right. This implies I wrote LHS as it is, f dash of x is equal to, come to RHS, the first term is d by dx of 3x. Here, if you observe, 3 is the numerical coefficient. You know that numerical coefficient can be written before the differential operator. So I wrote 3 before the differential operator because it is a numerical coefficient. Understood that point, my children? Do you remember that? Right. So 3 into d by dx of, what will be left there? X only. So d by dx of x. Understood this first term, my children? Right. Plus, come to the second term, d by dx of 17 is there. What is this one? 17, constant. D by dx of any constant. What is the value of d by dx of any constant? 0 only. Do you remember that formula? Yes. Because d by dx of any constant is equal to 0. By using this formula, we wrote the value of second term. Understood this step, my children? Right. This implies we wrote LHS as it is, f dash of x is equal to, come to RHS, first term, 3 into d by dx of x. What is the value of d by dx of x? Yes, 1 only. Okay, my children, understood this first term? Right. We are not writing second term because it is plus 0. We can eliminate. No need to write this second term. Okay, my children, because it is 0, plus 0. Because d by dx of x is equal to 1. By using this formula, we wrote the first term. Understood this step, my children? Right. This implies what we get? F dash of x is equal to 3. What is the value of f dash of x here? 3. Is it a positive number or negative number? Yes, it is a positive number. Being it is a greater than 0. Means here we got f dash of x is greater than 0 for all x belongs to R. Because there is no variable to substitute any real number here, so automatically it is already it is a positive number. So it is always positive number for all x belongs to R. Therefore we can say that f is strictly increasing on the set of real numbers. Understood, my dear children? Right.